Okay, today we're going to be talking about how we calculate concentration. So, up till now, we've looked at concentration in terms of saturation. So, we use the terms saturated, unsaturated, and supersaturated. These are terms which describe solutions, but they don't really tell us a whole lot because saturation point is dependent on what the molecule is. So, we can have a solution that's saturated of one compound and an unsaturated solution of another compound, but they actually have the same concentration. So these terms don't allow solutions to be compared quantitatively, meaning using numbers. It's like saying a material is heavy or light, okay? We have to compare it to something to say that it's heavy or light, but there's no numbers to back this up. So you are just making observations. You're not really having numbers to back it up, which in science we like numbers. So there are many different methods for calculations of concentration. Each method is valid and has its own use, and in some instances we use certain methods over another. So the most common used is molarity. Others include parts per million, parts per billion, and molality. We're going to first talk about molarity. Molarity is how many moles of the solute are dissolved to make how much solution. So we don't really care about how much solvent is added. We just need to know how much total solution we end up with. So to find this, we have moles of solute divided by liters of solution, and that equals molarity, which is denoted with a capital M. That's how we show the units for molarity. So to review, to convert grams to moles, we divide by the molar mass. So you're going to need that. That we learned back in the chemical reactions unit. I believe it was chemical reactions A. Another quick piece of review, notice that this says you need liters of solution. So our unit for our volume always has to be liters. If you're given milliliters, you need to know that 1,000 milliliters is equal to 1 liter. So 2,000 milliliters would be 2 milliliters. 1,500 milliliters would be 1.5 liters. So an example problem, what is the molarity of a 3,000 milliliter solution made using 25.23 grams of CaCl2? The first thing we need to do is get our grams of CaCl2 into moles. So we set up our T-chart. We calculate the molar mass. I find the molar mass of my 1 calcium, the molar mass of my chlorine, and multiply it by 2 because there's 2 of those chlorines. I get 110.98. That goes on the bottom because I'm trying to cancel my unit of grams here. So grams have to be on opposite sides there. This is equal to 1 mole of calcium chloride. And when I do that math, I get 0.22733 moles of calcium chloride. So 25.23 grams of calcium chloride divided by 110.98 grams of calcium chloride is equal to 0.22733 moles. So once I have that, I've got the top of this. Now I need to figure out my bottom, liters of solution. Now I'm given 3,000 milliliters, so I need to convert that into liters. 3,000 milliliters is equal to 3 liters. Now I've got the top and I've got the bottom, so I set up my equation. I do the math and I get 0.0758 molar solution. So if we were to say this out loud, you just heard me say it, 0.0758. This capital M stands for molar solution. And then we could even go as far to say it's a solution of calcium chloride. The next one we're going to talk about is molality. Now molality, if you did level 4 of solutions A, you learned how to calculate molality. It's less common than molarity, but it is used in some calculations, so it's important to know. Molality is a little different. It's the moles of the solute, which is the same, over the kilograms of the solvent. So now we're not caring the volume of solution that we're making. We're caring about how many grams or how many kilograms of my solvent do I add to my moles of solute. And that gives me the molality, which is denoted by a lowercase m, okay? So when you're talking about a concentration, if you see this lowercase m, know that it's not meters. That can be kind of confusing because we actually use that same unit to describe it. Quick review again, 1,000 grams equals 1 kilogram. So if you're given a certain number of grams of solvent, you need to make sure you convert it into kilograms. our example problem here, what is the molality of a solution made using 63.02 grams of Mg3P2 dissolved in 2,000 grams of water? So I've got my grams of my solute, and I need to convert them to moles, same way we did in the last slide. Finding the molar mass, that goes on the bottom, it's equal to 1 mole, and I do the math. Okay, 63.02 grams of Mg3P2 times my 1 mole of Mg3P2 divided by 134.87 grams of Mg3P2. This gives me 0.46726 moles of Mg3P2. Then I need to figure out my kilograms of solvent, because I figured out my moles of solute. Now I got to figure out kilograms of solvent. So I have 2,000 grams of water. I know that 1,000 grams is equal to 1 kilogram, so 2,000 grams has to be equal to 2 kilograms. Now that I've got my top and bottom figured out, I plug them into my equation, do the math, and I get 0.2335 lowercase m solution. And if I were to say this out loud, I would say 0.2335 molal solution of magnesium phosphide. For parts per billion and parts per million, we're going to talk about them in the same way because it's only the last step that really changes them. If a solution is a billion or a million parts, how many of those are solute? So that's kind of what parts per billion or parts per million means. If I have 1 out of every million pieces is my solute, then I have a 1 parts per million solution. If I have 10 parts out of my 1 million parts are my solute, then I have a 10 parts per million solution. Similarly, if I have 10 parts out of a billion parts, then I have a 10 parts per billion substance. These are used for much smaller concentrations, so you'll often see like water quality testing done with ppm or ppb just because the concentration is so much smaller. These are also easier to calculate because there's typically less converting because we don't actually need moles or any specific thing. We just have to make sure that the top and the bottom of this, so my parts here, are the same unit. So I could have milliliters and milliliters. I could have grams and grams. It doesn't matter what it is. It just matters that they're the same unit. So our example here, if I make a solution that is 290 drops of lemon juice and 710 drops of water, what is the concentration in parts per million? So to do this, I'm going to take my 270 drops of my solute, that's my lemon juice. I'm going to add these together, these two numbers, 290 and 710, to give me my 1,000 drops of total solution. So what I'm essentially saying here is that out of my 1,000 total drops, 290 of those were my lemon juice. I'm going to multiply this by 1,000,000 because I'm wanting parts per million, and that gives me 290,000 ppm of lemon juice. Now if I wanted parts per billion, the only thing that would change is I would multiply by 1 billion. Okay, so you can see where this will allow for much smaller concentrations. 10 parts per million or 1 parts per million is much smaller than this because really 290 drops of lemon juice out of 1,000 is not that many. So this really just allows you to calculate concentrations at a much smaller level. If you have any questions about this, make sure you ask your teacher. Otherwise, you can move on to the practice activities.